So there's a difference between the words implicit versus explicit. So we're going to talk about these as we get into what we call implicit differentiation. So an implicit equation is one that just basically relates x and y, and that doesn't necessarily mean that y can be written as a function of x by the definition of the word function. All right. Some implicit equations can be written explicitly, but not necessarily all of them, obviously. All right, and so I've written down two examples of what would be considered implicit equations. Whether or not I can solve for y as a function of x is not relevant. Just the form in which they currently are shows them implicitly, right? Because I'm not showing y explicitly written in terms of x. I don't have a y equals and then a function of x. All right, so I've got x plus y squared equals 3xy. So I've got y on both sides of the equation here, which, it doesn't have to be that way, but I do see y twice and y is not isolated. Same thing here. I have the sign of x plus y. This one's even worse because it's inside of a sine function. The y is inside of the sine function. And that's equal to 2x plus 3y. Again, there's no isolation of the variable y here. So these would be considered implicit equations that relate x and y together, okay? An explicit function is what we would normally think of, y equals f of x, where y is written explicitly in terms of x, meaning I have y equals, and then the rest of my terms on the opposite side of the equation are all going to be in terms of x. Terms meaning things I'm adding and subtracting, okay? And remember that the definition of a function is that for every x in the domain, I'm going to get exactly one response for y in the range, okay? And so most of you will think about that as like you're passing your vertical line test when you look at it graphically speaking. All right, now these are two examples of explicit functions. Y is a quadratic function here. So the graph of that would be a parabola, all right? And here y is a trigonometric function, in this case cosine. While there's stuff inside, it's going to have the basic properties of the cosine curve, obviously composed with the x squared plus 1 piece. All right, so these would be examples of explicit functions where I've isolated y and everything on the other side of the equation is all in terms of x. So what we're going to do is just look at a couple of examples of determining whether or not we can take something that's already in implicit form, right? So I have two equations here. We'll do these one at a time, obviously. They're both written implicitly, meaning I have x's and y's on both sides of the equation. I haven't isolated y in any way, but I want to know if I can write y as an explicit function of x. All right, so we're actually going to tackle this the elementary way to practice our algebra skills first. We're going to make a valid attempt at algebraically isolating y. All right, so for this guy here, I see that I have x squared plus y squared equals 4. So I'm going to go ahead and subtract the x squared to the other side in an attempt to isolate y. So here I would have y squared equals 4 minus x squared. But then to isolate y, I would have to take the square root. And the problem with that is when I take the square root of both sides, I need plus or minus the square root because the y that I had in the line above could have been positive or negative, and squaring it would give me the same result. So I have to make sure that I have that plus or minus there. And the reason why now I cannot say that y can be written explicitly in terms of x is because here, if I plug in an x value other than 2, I'm going to get a positive value and a negative value, which means I'll get 2 y values for every x other than 2 or negative 2. So that breaks this rule that for each x in the domain, there is exactly 1 y value in the range. That won't happen here. I'll get 2 y values in the range. So y is not an explicit function of x. I'm just going to go ahead and say that. But then I want you to think about y. What's going on here? What is this? Well, this is the circle with center at the origin and a radius of 2, because when we square 2, we get 4. So when I look at that, I realize that, hey, any circle is going to fail the vertical line test at all points except for its left and right vertices. So here's my circle, right? The upper half of the circle is the positive square root of 4 minus x squared. The lower half of the circle is the negative square root of 4 minus x squared. That's where the plus or minus comes into play. My positive y values, my negative y values. And so basically, I'll just put 1 point here, 2, 0. Basically, if I were to look at this graphically with the vertical line test, it fails. So this is not a function, not an explicit function, excuse me. All right, so let's go ahead and look at the other example now. So let's go ahead and make a valid attempt at isolating y here. So for this equation, I want to try to get the y's on the same side if I'm going to try to isolate them. So let's go ahead and subtract the 3 over, sorry, the 3y. So we have x squared y minus 3y, and that'll be equal to, I'm left with negative 2x over there. Again, if I'm trying to isolate y, but I see it in both terms here, right? I only want to see it once. How about if I factor them out? So I have y times the quantity x squared minus 3 equals negative 2x. Still trying to isolate y, but I'm multiplying it by x squared minus 3. So it's probably a good idea to just divide both sides by x squared minus 3. And I get y equals negative 2x over x squared minus 3. So I was able to isolate y, and for that matter, any x value I plug in here is only going to give me one y value. Okay, so in this case, yes, y can be written explicitly as a function of x. Okay, so far we have, nope, this guy, the furthest I can go is implicit relationship. Here, yes, I can write y as an explicit function of x. And then I've got 2 more examples I want to look at for a little bit more algebra practice. All right, so for this one, the y that I'm trying to isolate is stuck underneath this square root. So the way that I would get rid of the square root or eliminate the square root is to square both sides. So I'll have 2x minus 5 quantity squared equals, and if I square the square root, it does cancel x minus y. I'm still trying to isolate y, but I don't love the fact that it has a negative coefficient. So I'm actually going to go ahead and add him over, which didn't really isolate it, but now I have y plus the quantity 2x minus 5 squared equals x. And if I'm trying to isolate y, I can just subtract that term, that squared term, over to the other side. So I have y equals x minus 2x minus 5 quantity squared. Now, I don't have to go any further to realize that, yes, this is going to be an explicit function of x here. If you did want to go a little bit further, you could multiply this out, but what you'll end up getting is a quadratic function. Okay. But yeah, so here, in any x value I plug in is going to give me one and only one y value. So this can be written explicitly. It's in implicit form to begin with, but we can write it explicitly. Okay, this one's a little tricky. There's not much I can do here, and here's the reason for it. I have y squared and y to the first. So because I have y to 2 separate powers, nothing algebraically that I do is going to allow me to isolate the y. All right, because even if I factor the y out, right, I still see him twice. In fact, that's even, it's not going to help me at all because I can't eliminate either one of those y's. All right, but your telltale sign here is really anytime you're raising y to an even power, you're pretty much in trouble because you know that y could have positive or negative values as results from any X value substitution. So this would be a situation where I can't get out of the implicit form. I'm stuck there. And so what you're going to have to be able to do with this knowledge is know whether or not you can take derivatives in the way we've been doing differentiation, which is by, your basic product, quotient, chain rules, and your rules and formulas for derivatives. Or if you're going to need to use what's called implicit differentiation, which we're going to be discussing in class next.